So we're going to start performing the forward pass of our input image, in this case X, our padded image of 1 by 3 by 640 by 640. So here we're just defining two empty lists, Y being the output, and DT, we won't be using DT because it's right here and profile is to false, but we'll create it anyways. And here in this for loop, we're going to be looping over all the modules within self, which is detection model, modules, and then model, sequential, and then one more time, modules. So these are all our stages within our neural net, which of course correspond to our architecture diagram, as you can see here. All of the stages, starting with stage 0, 1, 2, and so forth. As you can see here as well, 0, 1, 2, and so forth. So let's do a parallel path between VS Code and our Colab environment. If you haven't opened it, just go ahead and open our Colab notebook. And the first thing we're going to do is load detection model. Let's mount our drive first. We just came out of the previous video, so it's already mounted. Otherwise, just click your Google account and then continue. Here, we're going to load our YOLOv5 PyTorch model. And then here, basically, you can see that our CKPT is the dictionary that we saw a few videos ago. We're just loading it here so that we have the same conditions in our Colab as we have in our VS Code. So now let's scroll down. And now we're going to convert it to float 16, similarly as we did in our VS Code. And then here, we're just going to send it for evaluation and fuse the layers. Again, we did these steps in much more detail in previous videos. Here, we're just defining these variables. And now here, given that self is the detection model, when I call self.model, I'm actually inside sequential. And here, when I run this loop, I'm going to print every module within sequential. So let's run this. And you can see that we have conv, and C3 in the same way that here we have conv, C3, and so forth. And then similarly, if I run this, but I call the m.f, then I'm going to be calling the property f within each module. So let me run this first. You can see that we give -1. Here we get a list, -1 and 6. Here we get another list, another one, and then the final one. Let me show you what these values are in VS Code. So if we pick up, for example, the first one, you can see that f is -1. And these values basically are coming from this YAML file, where in the architecture, we defined where our tensor is coming from. So in this case, the input is coming from the previous layer, in this case, the input image. And then the input to this second convolution, or index 1, is coming from the previous step. And similarly for all of these ones. Because in this case, the tensor is flowing sequentially. The output is the input to the next stage. However, there are some stages that the output takes two paths. It goes downstream for the backbone, but it also goes sort of sideways to the head. If we want to use the same terminology, use here. So in this case, in the head, there are going to be some stages where it gets input from two different places. So for example, this concatenation step is this one right here, where it gets input from the previous step as well as from a step, in this case, 6. So 0, 1, 2, 3, 4, 5, and 6. And actually, we're looking at this concatenation, not the one above. And then similarly, the next concatenation takes input from the previous stage as well as from stage 4. 0, 1, 2, 3, and 4, which corresponds to this one. Previous stage and then stage 4. And then similarly, this other concatenation right here, this one right here, and then of course the output, the last class, which we'll go over in much more detail, also takes input from here, and here, which corresponds to stage 17, 20, and 23. So stage 24 takes 3 inputs, and that's what the F means. It's basically taking this first value here. In some cases, it'll just be -1, and in other cases will be different. And here, we're checking if the value is different from 1. Well, in our case, if we step into this, M is our conv class, our first operation, and given that F is -1, we'll step over that. Profile is set to false, so we'll step over that. And then here, we're going to perform the forward pass. Essentially, we're going to be feeding our input image or tensor to the conv class. So let's step into that. And we are inside the conv class, of course, in the forward fuse, because in a previous video, we fused the convolutional weights as well as the batch norm weights and bias. So that's why we're here. And self conv has these values. It has 64 channels. The size of the kernel is 6 by 6, stride is 2 by 2, and padding is 2 by 2, which of course shows the same values as in our architecture diagram. So when we run this, we're going to be feeding the input image to this convolution operation, which was defined here, which is a conv2d function. And the inputs are the values that we have here, where you can see that C1 will be 3, C2 will be 64, K, this is the kernel size, 6 by 6, S will be the stride, 2 by 2, and then P will be padding in our case, this is 2 by 2, although it could be none. And then group 1, and then dilation 1. We'll talk about this one in just a moment. So we'll run this, and then we'll perform that convolution operation, which perform both the convolution as well as the CILU activation in one step. Now, when we run this, X, which right now has this value, will be updated with that convolution operation. So X will be updated. So let's run that, and you see that X will be modified to now these values. And then here, we're going to append to this empty list the values only if those are going to be needed downstream. So in self.save, you can see that we have 4, 6, 10, 14, 17, and so forth. Again, these correspond to the stages. For example, 4 would be this one, 6 will be this one, and this one will be used, as we said, downstream in future operations. So we want to save those tensors so we can retrieve them quickly when we're performing this forward pass through the neural net. So in this case, we don't need to save this one because the tensor is going to be modified. And then we'll definitely need to save this one because we will need it downstream, as well as this one, etc. Given that we're in stage 0, you see index 0 is now here. So Y, when we run this, will just be the value none, since we don't need to keep track of that tensor.